Yo, what up, people? Today I'm going to make a video. I'm going to do something really ambitious. It's either going to be a terrible disaster or it's going to save the world. So I've been working with Docker for several years now, and I've always tried to help find strategies to help onboard new folks to containerization. And when I go online and I search for Docker containerization, I'm always presented with diagrams of hypervisors and kernels and apps and libraries, dependencies, and then they like compare that with the Docker version, which is like one kernel and libraries and all those things. And I find, yes, that's the most technically correct way to explain what Docker is. But if you try and explain that to people, it's very hard to use that to onboard them because they cannot compare that diagram with what they're used to. In my experience, also, majority of people who onboarding containers are Windows users, and Linux is pretty much casting a shadow onto a lot of this because containerization is a Linux concept. So I'm going to try something really ambitious here, and I'm going to explain containerization and try and simplify it from a Windows user perspective. So for the sake of simplicity, I'm going to assume that this is my Linux host, and I know it's Windows, but let's pretend for a moment that it's a Linux server so you'll understand and grasp the concept. And on this host we have a kernel. Now Windows also has a kernel. The kernel is in charge of all these processes, and for example we have Chrome running here, and Chrome is just a process. Chrome has access to CPU, memory, disk, and network, and yeah, it has access to all the resources here. Now Linux also has a task manager just like this called top or htop, and on a Docker host like this we have a Docker daemon installed, which is over here. This is the Docker daemon. Docker daemon is responsible for all the containers that we run. It supervises them. So to interact with the Docker daemon, we need the Docker CLI, and we need to use command line. Now Linux, everything is command line, so we need to start working with the command line. Now in a traditional world, when we wanted to start Chrome, we would click on start, we'd search for Chrome, and we'd click on Chrome. This will send an instruction to the kernel to start up a process called Chrome, and then that's when you'll see it in your browser and it will come up in this list. Now in the Docker world, it's exactly the same thing. The only difference is we do the Docker run command. And yes, in a Linux environment, you can totally run Chrome in a container. Now, when we do this and we run this container, we pass this command to the Docker daemon. The Docker daemon will then send an instruction to the kernel to launch a process for Chrome, and Docker will then supervise that process and basically watch it. If that process dies, Docker will stop the container. If we kill the container, Docker will kill the process. You want to take note here that running the container through Docker is no different than starting the process directly from the kernel, or in our case through the start button over here. The benefits here is that starting a container is insanely fast comparing to VM. It's only a few microseconds slower than actually starting a native process. Now, when we take a look at the Linux Task Manager, or top or htop, the Chrome process will list there whether it's a container or not. So the other processes and the operating system is oblivious that it is a container. That also means that our process is not running in Docker. People always say, yeah, I'm running my app in Docker. It's not actually running inside Docker. The process is running on the host just like any other process. The difference is that Docker is supervising this process using special Linux kernel features. So let's talk about these features. Okay, so for a second, I'm just going to create a barrier here to help us visualize. Now, in the Linux world, when we do Docker run, Docker creates a container with an ID. A container is just an object to help Docker stitch all the magic together, just like you have a customer ID in your database. Now, I'm just going to make sure this container is not running. Cool. And if I run an Nginx server, that you can see Docker created an ID for us. And what it also does is locally here, we have a volume. Now Docker has a var-lib docker volumes folder on the host. I created this manually, so it won't be there on a Windows system. This is only to show you what happens on Linux. And Docker will create a folder here for the container ID. And that folder is mapped through a virtual file system to the container, which is running up there. And the process is basically attached to that virtual file system. So all these files here are within the container, and the process can only see these files. So this is where the encapsulation or the containerization starts to happen, because now this process or container only has access to these files and cannot access the files on the outside world. So it cannot access these volumes, these other folders on the host. And that is because Docker started our process by attaching it to that virtual file system. Now the benefits here is that when we are in a container, we can install stuff without affecting other containers. Like traditional software, we can run different versions of Nginx, we can have different versions of PHP or Java installed in that file system, and it won't affect other containers. Now, what if I wanted to bring in external files? Like let's say I have some external network storage, some RAID storage or network, like a database file or an external config file that I want to bring into the container. Now let's say we have the storage folder here, and I have some storage and there's a test file that I want to mount inside my container. Now what we can do is Docker allows us to mount a volume into the container. So if I make sure this is not running and I start that up, you see we use the volume specification and we're mounting that storage folder into the container at my storage. So now when we go into that container using Docker exec, we can see once we're inside and we do ls, the my storage folder is available to us, and we can go inside there and we can see the test file is available to us. That is because Docker has mounted that external file from the host, has mounted it as a virtual file system inside the container so we can access it. Our process currently has access to all the memory and CPU. So our Nginx and Chrome has access to all the CPU on this host and memory. And Linux has a feature called Namespaces and C Groups, and this is what the Linux kernel uses to control what a process can see and use. Now this is an old technology. It started the journey of containerization, and Docker is leveraging this feature, and it gives us an option to specify memory and CPU when we start up our container. So for example, if we specify the CPU flags, I say I want 1 core and I want 512 megabytes of RAM. When we start up this process, all of a sudden we will send this to the Docker daemon. The Docker daemon will send the relative C group and namespace instructions to the kernel and launch our process with those C groups and namespaces for us automatically. So now we can see that our process has launched here, and it can only see one CPU core, and it only has access to that compute. The benefits here is that we can run more than one process now on the host and get better isolation. With virtual machines, every machine has its own kernel, and that's a lot of operating system overhead. We don't want an operating system per process, and that's kind of what we got with VMs. What we do want is we want to share one kernel and use the features to get proper process isolation at the same time. So using this, we can run more processes all isolated under one machine and save money on compute. Let's talk about the Docker network. Every container that is created here runs on its own virtual network with its own IP address separate from the host. By default, containers cannot see each other unless they're on the same network. Now, to make containers talk, we can add them onto the same network through the docker run command, and there is a flag called --net, and we can pass a network in. When we do that to multiple containers, these containers can access each other using the host name or their container name, which is basically the host name. Alternatively, containers can link to each other. So if we use the docker link flag, we can say, I want to run a container, its name must be container 1, and I want to link it to container 2. That means these containers can now talk to each other, and Docker will bridge them through the virtual network. If you run web applications, you may be interested in port mappings. Now, we can tell Docker we want to make our containers accessible through a port number on the host. Docker will map this host port to the container port that we specify. So, if I take my example of my Nginx image, and I just make sure it's not running, and I run that and I pass in the port flag, I can map port 5000 to port 80. And what will happen now is Docker will bridge that port. So if I go to my browser, we can see I'm running Nginx on port 5000. So any traffic coming into the server on port 5000 will hit that container on port 80. The beauty about this is developers can all just stick to one port. They can code up their applications to all run port 80, and as long as we have unique ports on the host. And the benefits of this is that we can now isolate the network for the containers, and we can run all our containers on the same port. As long as the host port is unique, otherwise you'll have port conflicts. Now, this is where container orchestrators like Kubernetes come in, because they take care of host ports to prevent collision of ports, so we don't have to worry about it. Now, last but not least, the Dockerfile. Now, if I go into the Dockerfile is basically the traditional provisioning script that you would normally see, that you'd code up and you'd run on a base operating system that spins up your application on your production server. Now, the Dockerfile always starts with the from, and basically this can be an operating system like Ubuntu, Debian, or Alpine, or it can be another image that you want to extend. Now here I take an example of an Nginx image that I want to extend, because I want to use Nginx as my web server. I pass in a config and I pass in some HTML file to make my website, and that's pretty much it. I build that, and that produces my Docker image that I can run as a container. Now you can also bring in Apache server or some PHP or Java app. You can also bring in an SDK like .NET Core or Golang. You can compile your app inside here using run statements, and you can produce binaries, and then also bring in source code with the copy statements too that you can compile. And then those output binaries, you can then use the entry point or the command inside the Dockerfile to actually run those binaries, and that could be your web image or your microservice. And when Docker builds this, it'll evaluate this file from top to bottom and run this in like a temporary container to produce an image. And each layer here, each line becomes a layer, and each layer is hashed, so that helps Docker to detect if something has changed. And if a file does not change, Docker does not rebuild it, and it simply uses the cache layer, and this helps speed up build times dramatically. Also, if only one file in this web server changes, Docker will evaluate from top to bottom, notice that the hashes are all the same, but then will only calculate the diff of the hash in this one, so it will rerun this step as a layer and produce a delta hash for that. So this helps optimize the storage for storing our Docker images, and Docker is really smart in how it stores versions of images and pretty much only stores deltas. So this prevents it from storing duplicate images onto the host. So sorry about the long-winded info. I try to condense it all. I hope that made a lot of sense and some of the concepts are more clearer to you guys. Well, anyway, that's it for this video. Please leave a comment down below and like and subscribe. And let me know what you guys want to see in the future and how I can probably clarify some more things.